Okay, so this is chapter 3, and so far we covered the basics of electric circuit, starting with Ohm's law and power law. So we have loads, which are resistance, things that consume electricity, and we have voltage, which is also electrical potential. So if we have higher voltage and lower voltage, we have electric potential, and things always try to equalize. So the higher potential will move into the lower potential, and that will generate flow, and that's called what? The flow of electricity. Current. So we talked about current, we talked about voltage, resistance, and power. And power is the flow. Power is the flow of current through an electric potential. That's why it's power equal voltage times current. This week we'll try to cover resistances in parallel and series, which is the basis of simple electric circuit. So when we say circuit, it means it's a circular thing, has to be continuous, otherwise it's not a circuit. So these are the topics we'll talk about: the basic concepts of electric circuit, what do we need to have a circuit, what actually constitutes a circuit, the two types of circuits, series circuit and parallel circuits. This is the basis of all circuits, and it could be either just in series, or it could be just in parallel, or it could be a combination. So we'll talk about that and see what is the characteristics in terms of Ohm's law and power law. So again, we have those two laws that governs our basic electricity, and we'll see how those two types of configuration will affect our circuit. So what kind of circuits do we expect in HVAC? We'll talk about that as well, and how does it affect the power consumption, or also our control. So we'll talk about how do we calculate for each one of those circuits, how do we calculate the current, resistance, and electromotive forces, which is what? Voltage. So for each one of those circuits, we'll do the Ohm's law, and we'll see how does it differ. We calculate the current, resistance, and voltage for parallel circuit, and also we can do a combination. So we'll spend some time into the theory today, and Friday we'll do some practice problems. And I put some practice problems on the blackboard for you to try and see how you do.
So we're going to do this Friday, right?
No. The practice problems?
Or no, the homework?
The homework we'll do Friday.
All right.
But the practice problems we'll work on all throughout next week. So these are the key terms we'll touch base on. Closed circuit, what does that mean? We have a complete circuit. Control circuit. A control circuit basically have some kind of switch or an input that will open or close a circuit using a switch. So a thermostat is a switch. It closes the circuit mechanically or sometimes electronically if we need to energize the AC. The circuit is just a common name. Open, there's not continuous path. So I'll draw a circuit. This is a voltage source. Where do electricity move from? Negative to positive or positive to negative?
Negative to positive.
Negative to positive, excellent. So current goes all the way here. We have a switch. We have a load. So this squiggly line here is the resistance.
The thermostat,
This could be a thermostat. No, this is just a
24 volt.
resistance.
Thermostat.
Not necessarily, but it could be. So when I put when you see the squiggly line, it means it's a resistance. It could be a heater, could be a light bulb, could be anything else. A thermostat is usually a switch. Thermostat will look like this. That's a thermostat. It expands and contracts. Load, and we go back, and that's in this position now. Is it open or closed circuit?
Open.
It's open. Once the switch is closed down, it's a closed circuit. We'll talk about series circuit, series parallel circuit, which is a combination, and we'll talk about voltage drop. So electrical system is usually composed of few components and a circuit. What do we mean by the terminology? We want to explain that what does the terminology means before we can move on and have some problems. So first thing is parallel circuit. What do we mean by parallel circuit? That means that there's more than one path for the current to take. So this is our current here, right? So if you see the current coming all the way, we call it I1. If it diverts and forks, so it will divide into 3 little currents, or 2, or 4, or 5, and those will get equal amount of current to start with, A2, A3, A4. This is considered parallel. So whenever the current coming in diverts and have more than one path, it's parallel circuit. You don't have to see them being parallel this way. They could look something like that. This is still parallel. The reason they say parallel is because the current will divert into parallel paths, so you don't have to see it visually as parallel. So that's one example here. I'll draw some resistances here. And eventually those paths have to meet again at some point. So that's a parallel circuit. In series, it's much simpler. Basically, each path follows the others. So that's parallel. And in series, well, one path, A1, that will go through 1, 2, 3. Same thing, and same current. We'll keep following only one path. Any question about that? So what do you think a combination will look like?
Only one circuit.
Yeah, so I'll make this into a combination now. So I'll have one resistance here. What is the squiggly line again?
Resistance.
Resistance or a load. So anything that uses electricity, we consider as a load. But when you see a squiggly line, that's a resistance. It could be a light bulb. We can put a light bulb in there. And every electrical equipment or component has its own symbol. So I'll put a small divergent here. And that will be a parallel circuit. So are these parallel?
Yeah.
What about these two?
Series.
They're in series. So this is called a combination circuit. And are these two in parallel with these two or in series? Series, correct. So these two are in parallel with each other, but since they have the same current path with the other two, then they are in series. And we'll do more examples to see how this works. Any questions so far?
Yeah, so the resistance is what sends the electricity the opposite direction?
No, that's the voltage. That's the source. So when you have a battery, that's your volt.
Right.
That's what gives you electricity, voltage and current. And the resistance basically is what's using that current. Could be a heater.
Who's using it?
Yeah.
Oh,
Loads. They use the electricity, the current. A light bulb, a heater, a battery is being charged. So for example, when you plug in your phone, you're completing the circuit and your phone is becoming a load. It's using electricity. So if you're loading on the system, and it's basically a load. Voltage, the battery supplies the voltage. If there is no supply, there's no load, the circuit is dead. If the circuit is open, no connection, circuit is dead. It's not alive. Once you connect it, the circuit is complete, and we'll start using some voltage. Questions? We'll do more examples on Friday, but let me go through the material and at least the terminology. So we understand what that series mean. The current has only how many paths? One path. And for parallel circuit, it has more than one path. Could be 2, 3, 100, whatever you want. So if you look at the Christmas tree lights, those little light bulbs, if you wire them in series, if you take one out, the whole thing dies. Correct?
Yeah.
But now they wire them in parallel. So you can take one, you can take 3 out, and they're still running. And that also has some advantages, and we'll see how is that. Think about circuits, the path. Closed circuit is basically when you have complete loop, there's no switches. An open circuit is, this is open. There's no complete path, there's an opening in the circuit. So we must have a complete path for the flow. Source of electron flow, which is basically the current. And we have a load, otherwise what is the point of the circuit? Because the wire going in loop, there's no point for the circuit. So let's follow the path of electrons here. If I take this, if this load breaks, and this is closed, do we have a circuit or not?
Yeah.
We still have a circuit. One of them is broken, but still there's a circuit, there's current, something is running. These 3 components are running. If this one is out, do we have a circuit?
No.
No. So it's open. Now it's closed. If we take this one out, again, there's no path. Why do we need to know this? That's the basis of troubleshooting. So you see some voltage, you see some current, but you want to know which component actually is not functioning properly. And again, we all have to have the 3 components for Ohm's law. This is the resistance, called R2, R1, R3, R4. This is the voltage. This is, I'm gonna call it A, to be consistent with the diagram. And Ohm's law apply in all circuits. So you're always going to have amperage if you have a circuit, resistance, and voltage. Any questions so far about the terminology at least? As we go along, it will get clearer. So this is a simple circuit with a plug and a load. There's not even a switch, as simple as it gets. It's a light bulb. You plug it in, and the circuit is complete, and there's something using the load. So that's a basic circuit, as simple as it gets. This is the simplest. There's only one path. Why do we need to use it? Remember when we did the lab and we wired all the switches? Was it in series or in parallel?
Series.
They were in series. We had 4 switches. Why? Each one of those switches represents something. One of them is firomatic, which means what? If there's fire, it will cut off the circuit for the entire board. They had a fuse. That's for load. If this one was cut or shorted, the circuit will not be energized. The 2 other ones are control. So there are 2 things, main purposes for series circuit. What are they? Control and
Load.
safety. Those are the 2 reasons we use series circuit. Because if one of those controls is out, the whole circuit is out. Otherwise, what is the point? I'm not controlling that circuit. So I'll write it down here. Series circuit. Two purposes. Safety. What do we mean by safety? That's the firematic, that's the fuse. If the system overloads and becomes unsafe, it's taking too much amperage, we cut off the power to the entire circuit. And we do it in series, so the main supply, so that's why we put the safety coming out from the plug, right of the source, we cut off the circuit. So we put them in series with the entire system for that purpose. So remember that, 2 reasons for putting the circuit in series: safety and control. If we have 2 control switches in parallel, if one of them is out, the other one is going to be on. So you cannot control with 2 in parallel, you need 1 in series. That's an example for 3 switches in series or parallel. What's in parallel?
I was looking at 208, I thought that was.
I know, it's confusing, but always follow the current.
Yeah.
So line 1, which usually line 1 is hot, so they will say line 1, or they will say hot or black. Those 3 switches are in series. So this is a high pressure switch. So if the pressure in the system, I'm assuming it's going to be a steam boiler. If the pressure is too high, this will open up and it'll cut off the circuit from the entire control. If the pressure is too low, it will engage. If you notice the position is different, do you see the little differences here?
Yeah.
Yeah.
So the high pressure,
Inside.
this needle will go up to push up and disengage the circuit. The pressure is too low, it will again pull up and close the circuit. So this will disengage and this will engage when we have low pressure. The opposite action. So, and we can set the limits for both of them. And this is a thermostat. This thermostat again usually comes from the room. So if the room is cold, there's a call for heat. The thermostat will engage. So this is called a heating thermostat. If you look at the little bi-middle spiral here, do things expand or contract at heat?
Expand.
Expand. So this is usually closed, open. When it gets too hot, too cold, it will shrink. When it gets too hot, it will engage. We'll talk about thermostat in the entire chapter.
So the high pressure means when it's warmer inside, it'll switch off, and the
Yeah.
low pressure is colder, it turns
Yeah.
on, right?
Exactly. So, doesn't tell you much, but basically, we'll talk about thermostat. So these are all like control switches: high pressure, low pressure, thermostat. Sometimes a timer. It's also can be controlled as a switch. So all these are wired in series as control for the small circuit. Okay, here where it gets a little bit interesting, but don't let it get to you. So what happens to the, you might get a little bit confused with this in the beginning, but then it will make sense, and we'll do a lab in that to make it stick. Appreciate your head. Have confidence. So what happens to the volt? So the current drawn the same throughout the entire circuit, and the current will be the same. So what will happen? Remember the Christmas tree lights, right? We have one current. If you take one out, you cut out the current. So the current entirely is going to be the same. I'll explain to you why. But let's write it down so we remember. The current stays the same. Voltage will be depleted, but by the last load, you'll have less voltage than you started with, so you'll use up the entire voltage. So voltage will be used entirely.
So the more resistance you have in the circuit, the less voltage you're gonna have at the end.
Yeah. Resistance will add up.
Yeah.
On both sides, negative and positive.
Yeah.
So whichever one builds up more pressure, that's the one that goes through, right?
Yeah. So let's think about it. Let me explain that a little bit. So we're talking about the current in series, okay? So this is our series. I'll call this R1, R2, R3, R4. Okay? We all agree this is in series, right?
Yep.
Yes.
Anybody disagrees, have confusion, doubts? Okay. So the current is coming here, A1. Is it diverting anywhere? Is it going one path? How many paths?
One path.
One path, okay, we agree on that. We have voltage, we have current, we have resistances. So you always start with the resistances. What would you think the total resistance of this circuit?
Repeat that.
The total resistance of the circuit. If you wanna get the complete circuit
So the
resistance.
number is 1, 2, 3, 4.
Yeah, we add them together. So for the circuit, our total.
So you're just adding 1, 2, 3, and 4 together?
Yep. That's it.
Yeah, so 10?
No, we just have, that's the name. We don't have values for them yet.
Oh, okay, I was gonna say.
Find the resistance of R1.
It's not giving it.
I know, no,
Yeah.
just saying.
We'll have to put some
The
numbers.
numbers represent nothing except for the different.
Yeah.
They could be A, B, C, D, it'd be the
Yeah.
same thing.
Let's give it some numbers, if you want to. Let's say this is 1 ohm, 2 ohms, 0.5 ohm, and this is 3 ohm.
6.5 ohms.
So what would be 1 plus 2 plus 0.5 plus 3? That's 6.5 ohms. Everybody agrees?
Yeah.
Yeah.
Okay. The voltage. So the voltage you have 110. It will go through the first resistance. It will drop. It's not all going to be the same.
So it's gonna drop by the resistance?
By 15 minus,
It will drop by the resistance because we have.
oh yeah, yeah.
Let's think about it as. I'll do another example here that's can make things a little bit easier.
Here, one more.
So if we have a pipe, water pipe, okay? We have pressure. That's our voltage. If you open the first faucet, you'll have high or low pressure.
Aye.
High pressure. If you keep it open, you open the second one. Is it going to be the same or lower?
Lower.
Lower. So P at 1 will be higher than P2 and will be higher than P3. And at the end, whatever pressure is left over is used here. And you will return like with no pressure to the circuit. There will be no pressure. Use the entire pressure in the circuit, you will get very low pressure at the end. Make sense a little bit?
Yeah.
So we have flow, we have potential. Your voltage is your pressure. You use some of it here. You use more in here, more and some more. So we keep using the pressure until the end. We have no pressure. If we keep having faucets, at the end the last faucet will have no pressure at all. You open the faucet, there's no water coming out. Use the entire pressure. So the voltage for the entire circuit is being used. And what is the entire circuit using for voltage? We use Ohm's law. So the voltage is 110. And it will be used for throughout the entire circuit.
How do we figure out?
What is what? The amperage, we'll do that now. So we have the voltage, we have the resistances.
How do we figure out the resistance drop or whatever?
How much in each resistance? If you want, you can divide the voltage by each resistance, and you see the drop. You get the voltage, well, the first resistance, that will be your drop. Then you drop again. And actually, if you want to do that, you go with the amperage. So what happened to the amperage for the entire circuit? We said what it yeah, constant amperage. So the amperage for the entire circuit will be the same, and we'll do the calculation for that, which will be 110. We divide by the entire,
Divided by
Resistance.
6.5,
yeah,
16.92392.
92. And if I want to find what is the voltage drop, what is, of course, the first resistance, I have the amperage and I have the resistance, and I will just multiply that amperage by the resistance. So the first voltage drop is going to be 16.92 volts, and so on and so forth until the end. If you add them all, they're going to be the same. Let's do that just for experimentation. So V1, I will say it's 1 ohm times 16.92, should be 16.92. V2 will equal 2 times 16.92,
33.84.
33.
0.84.
84, and V3 will equal 0.5 times
8.46.
2. How much?
8.46.
6. And V 4. 3 actually.
50.76.
3 times 16.92. What is it? 50?
50.76.
If we add all these together, what do we get? It's supposed to be 110.
109.98.
Close enough, decimals.
Okay, I get it.
Are you convinced?
That makes more sense.
Huh?
That makes more sense.
Okay. Are we happy, comfortable with the circuit? So let's repeat, let's iterate. In a series circuit, there is one path for the current. What happened to the voltage? It gets used up. What happened to the amperage? Stay the same. What happened to the resistances? You add them up. So, one more time, without looking. In series circuit, what happened to the resistances? Add them up. Current? Voltage? Drops, depleted, whatever word you want to use. Okay, that was fun. Let's move on. we talked about that already. Parallel circuits. I want to use another board. Everybody done with that? This part. Everybody done with this part?
Good.
So I want to keep it, but I'll move over there. Okay. So now we'll do parallel circuits. Let's see what will happen. So first thing, the amperage. They add up. So the amperage makes sense because again the current is converting. 10. If you have flow of water, 3, 5, they'll get the same flow. We agree? So the amperage will add up. The voltage stay the same. Resistance?
Get the find the total resistance.
Yeah. But what do you expect is going to happen? I'll give you one rule. Remember that. The resistances in the parallel circuit will be smaller than the smallest one. That will reduce. Total resistance will be smaller than the smallest resistance in the and I'm going to underline in the parallel circuit. So in case I have a combination circuit, so if you get a number that's bigger than the smallest, you know there's something wrong in the calculation. And if you look at the combination circuit, don't go out looking at the other resistances outside the parallel circuit. Remain in the parallel circuit. I'll give you an example. This is going to be good rule to follow. So voltage stays the same, which is what to our advantage because everybody gets the same voltage. And current will add up, everybody will get their own flow, and the resistance will add up differently. I'll show you a method that I try to work out to make things a little bit easier. Luigi, can you go quick? So how do we add resistances on parallel? I'll show you a simple way to do it.
No, I think you meant,
Here's the clicker. I want to see how. Thank you. Okay.
That's backwards.
We did that already.
Backwards?
Yeah.
So remember when we said
Nope.
our total?
Nope.
yeah,
No, the picture. Yes.
This is was the total for what circuit? Series. So we'll put it the same way for parallel. Then we do something called F flip.
Wait, what is F?
I'll show you. So this means F for flip. You can use your own method, but I think this makes a lot of sense. Divide, add, then flip again. So FDAF, I'll show you how. I'll give them some values so it will make sense. So we'll say R1 is, for example, 1 ohm, 2 ohm, and 3 ohm. So when I flip a number, I get the reciprocal, or 1 over that number. Everybody agrees? I'll show you. So I will do 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Make sense? I'll divide. So since I don't have a number, this is what I'm looking for. I'll go with 1 over R total.
our total is 6, right?
Yeah. I'll put the numbers here. This is 1 ohm, 2 ohms, 3 ohms. So this will be 1 over what? 1? 1 over what?
2,
2? 1 over
3,
3. So if I divide that, I'll get 1 over R total. 1 plus, what is 1 over 2,
Two.
0.5,
Oh,
0.33. Then I'll do the add. I'll add this together. So I'll keep saying 1 over R total equals 1.83. If you're confused, raise your hand. Blink once. So first, we put in the numbers. You flip the entire thing, so everything gets flipped, 1 over whatever you get, and this, the total will also be 1 over the R total. I divide to get rid of the fraction and get a decimal. It's easier to work with decimals than fractions. This gets a little bit confusing. This is less confusing, right? You can put in your calculator 1 over 2, 1 over 3, 1 over 5, whatever one you get. Put the fractions to decimals. Then you add these three together. Again, you can use your calculator. So this is 1 over R total. So then you flip it again. So when you flip again, what do? Everything gives the bottom becomes the top. So it's going to be R total 1 over, which equals what? 1 over 1.1.
0.546.
That's going to be my R total. If
Is
you
that a lot?
notice the R total is smaller than the smallest one, which is 1. If you get anything larger, you did something wrong in this sequence. So put the resistances, just like you're doing in series, and do this process. The book has different ways to do it, but they make it only for 2 resistances, and it gets like a little bit more complicated if you do it for 3 or 4. And this actually in real life you have 3 or 4. So I think this way is just simple if you just follow the steps one by one. I'll do a lot of practice. So flip, divide, add, then flip again, and you get the total resistance. So the R is reduced, the voltage stay the same, and the current will add up. Okay? Let's get the camera back. So this is the parallel circuit. And you can tell the capacitors are in parallel with those switches. It doesn't look great actually. So again, same information. The current adds up. We all agree on that? And this is the calculation in the book, which I find very complicated. And this is what we just did on the board. So first, you flip 1 over R total to 1 over R1, 1 over R2, and so on and so forth, to infinity if you want. Then you divide and you'll get a number. That's only to get rid of the fraction and get decimals. You add those numbers together, so that you get 1 over RT, a number, then you flip that number. You can put that in a card and bring it with you to the exam. It's confusing. So you don't have to memorize that. But after a couple of practices, it will be much simpler to follow. So I have an example here. So you don't have to write that example. So what did I do? First thing, I flipped it. I put the layout just like in series. I flipped each one of them. I put the numbers in and divided. So you get fraction. From fraction you get decimals. We added them together. Then you flipped again. If you've noticed, again, it's smaller than the smallest one in the circle. Any question?
0.95 is over 1.
Yeah, no, 1 over that. You always divide from top to bottom.
It's divided by 1.
Yeah.
Flip it, no,
Yeah.
no, it's 0 divided.
And there's a little button in the calculator, actually, we'll get that for you. But if you don't have it, just do it the old-fashioned way.
What button where?
Huh? Probably in yours is going to be this one. This will flip anything. Okay, I'm trying to keep the math as simple as possible, and this is as much as it gets for this semester. We're done with math for this semester. We can't get master this. So we'll do a lot of examples. If you have any questions, come to office hour, ask me, or email me. And voltage drop. So when we have a combination, usually we have a control part of the circuit and a load part of the circuit. And what is the advantage again of having resistances in parallel? From what we noticed, huh?
Yes.
You have less resistance. So putting things in parallel is better for the circuit, between lower load. Another example in the book would be for things like it's actually actual. So are these in parallel or series? Parallel. Follow the traces of the line. What about these?
Series.
Okay. What about this load and this load? Parallel. These are in parallel with each other, and this circuit is in parallel with this circuit, and in parallel with this circuit. We'll do a few examples. Once you do a few examples, it will be much easier. We'll do some elaborate problem on Friday. Hopefully it will make sense. And if you can just remember the little rules here, that will make your life much easier. And bring any questions you have. Okay? Thank you.
Yo,